This is a Haloalkanes question. It's 15 marks and it spans from A all the way through to F. So I'm going to recommend you pause, try each section, and then once you've got right the way through to F, review your answers and see how well you've done. That'll give you an indication of whether this is a topic that you're confident on or whether it needs a little bit more work. So, parts A and B. Moving on to part C. Moving on to part D. Moving on to part E. And finally part F. Okay, so now you're done. Let's go through, take a look at the answers. First part of it is basic, straightforward nomenclature. I'm going to try and break this down step by step so we can see exactly where the name comes from. Now, the first thing to do is look for the longest carbon chain. It happens to be in a straight line this time, but it isn't always. So 5 tells us the name is based around pent. Now, from there, I look for anything that would give me a suffix. There's no double bonds, there's no carboxylic acids, so my name is going to end in ane. I've got pentane. I can also see that I've got 2 methyl groups which are branching off. So I know that they are going to have to be included somewhere. And I can also see that I've got 1 chlorine coming off there as well. Now, when we go about naming them, we also need to consider the positions of these. So I've numbered left to right, but actually I could have just as easily numbered from right to left and it would still give an identical name, and that's because this is a symmetrical molecule. So from here, I know that I have a chloro in the 3 position. I know that I have 2 methyls in the 2nd and 4th positions. My chloro goes first because your prefixes go in alphabetical order. I then have 2,4-dimethyl pentane, giving me the complete name. Moving on to part B, the first thing that I'm going to do is write out the molecular formula and from there work out what the molecular masses would be. I know they're going to be in the region of 134.5, but each isotope will be slightly different to that. Now, my 7 carbons are fixed. They provide 84. I have 15 hydrogens, mass number 1 each, so that takes me up to 99, and then it depends on whether it's a chlorine 35 or a chlorine 37, but the MR could be 134 or 136. Now that tells me that I know where my 2 peaks are going to be, but I still need to consider the relative abundance. Now we already know that 75% of the chlorine is chlorine 35. So that means it's a 75 to 25 ratio or a 3 to 1 ratio. So my abundance has to reflect that. And my line at 134 should be 3 times the height of the line at 136. Moving on to part C, and we have got mechanisms. And in this case, they're being quite generous because you're being told what the conditions are, but also what the product will be. The fact that you're told it's an alcohol makes this a little bit more straightforward. So in my mechanism, I'm going to do the mechanism before I name it. That way we can work out what the mechanism name is rather than just try to learn them as facts. But I'm going to start with the OH minus from the sodium hydroxide. Sodium's a spectator. We ignore it in the mechanism. And that is going to attack the delta positive carbon. Now the curly arrow, always electron rich to electron deficient. When the OH minus attacks, it does mean that it's essentially forming a bond between the C and the O. That would be 5 bonds, which isn't sustainable, so we lose the chlorine. Now in terms of naming the mechanism now, I'm going to highlight the fact that we've got the OH minus. It's got a lone pair which it can donate, which makes it a nucleophile, and that tells me that the mechanism is nucleophilic. And if I then consider what I'm actually doing here, my OH minus is taking the place of the Cl. It's replacing the Cl. You could say it's substituting the Cl. So it's nucleophilic substitution. And then finally, you need to draw the product. Now, it's nucleophilic substitution, so the OH replaces the Cl. Everything else is identical. And I've shown you where the 4 marks are there. The 2 marks, 1 for each arrow, 1 for the name of the mechanism, and 1 for the final product. We then move on to another mechanism question, still with OH-, but this time hot ethanolic, and it tells us that we're making an alkene. So let's take a look at what's going to happen here. I've got OH- again, as I say. This is actually going to attack a hydrogen this time. And it's a hydrogen on the carbon adjacent to the carbon that the chlorine is bonded to. Now, for that reason, when we talk about it acting as a proton acceptor, which is what it's doing when it attacks the H, it's acting as a base. Now, the remainder of this mechanism, if the H is gone, the CH bond no longer exists. So those electrons move in to the CC, forming a double bond. That again puts 5 bonds around the carbon where the chlorine is, so we lose the chlorine. And those 3 arrows are each worth 1 mark. Now you need to draw the product again, so we have got to be very, very careful here about the position of the double bond. It has to relate to where you've put it on your structure. And if I take a look at the type of mechanism, well, if we end up losing an H and losing a Cl, so a double bond has to be formed, we're removing things. You could say we're eliminating things. So this one is elimination. And if you ever end up with a double bond that you didn't have previously, it will be an elimination mechanism. You can see where the 6 marks are attained here. Moving on to part E, and we're actually doing some infrared spectra here, and a relatively straightforward infrared spectra question actually. Remember, you've got this data provided in the exam, so always do look at it. I am going to say straight away that it is an alkene, and there's 2 justifications for this. The one that immediately stands out to me, because I will always look for that broad peak on the left-hand side, is there is no broad OH peak. If there's no OH peak, it can't be an alcohol, so it must be alkene C. However, I can also check that I do have a peak at 1620 to 1680, which proves that it is an alkene. It's not a huge peak, but it is there, and it proves what we're working with. Finally, moving on to part F, and we want to know here, only in a 1 marker, why D reacts more quickly than A. The key thing to do in any question like this is identify all of the differences. And the only difference here is which halogen. So what we are looking for in this particular question is that the CBr bond is weaker than the CCl bond. That means it breaks more easily, which means it reacts more easily, which means that you can substitute it with an OH more easily.